Thank you. Okay, good. So today I just want to show a little bit about the work that I did with the Mujoko, which we can use for the simulation. Um, so maybe we can pin this message. Okay. Did you guys see? I think I missed it. Who knows this show? IT crowd? No? Some of the best television ever. So, because he just posted it. Has this ever happened to you? Well, today, dialing 999 won't get you emergency services, and that's not the only way it's changing. Most ambulances, faster response times, and better looking drivers, they're not just for emergency services, they're your emergency services. So, look for the new number. Okay, a bit of a tumble. Well, that's easy to remember. 011898811997725. So this is a very funny show about computer programmers in the company, and they do have lots of jokes like that. So that number seems rather long, so you may want to put that on fast dial or so. The NTNU number, not this number, of course, is a joke. It's not the emergency code in the UK. I'm sure is not like 20 digits long or something. Even though Aaron, but if you've never seen it, I highly recommend the IT Crowd. It's some very funny television. Okay, good. So let me.
Jackie, restart the recording, please.
Hello.
Yeah, please restart the recording, unless you already did.
Yeah, I'm starting the recording. It's running now. Yeah, it's recording now. Okay, so we will have to work on the groups a little bit later, but for now, to get you started, um, I will post the GitHub repository. So hopefully I can. And you want to install Mujoko, which is the latest, greatest simulator by Google, DeepMind, Google's DeepMind. Probably the most accurate physics that you can simulate on a computer nowadays. So we have Windows. And it's only 11 megabytes, so it's actually a very lightweight package for that, for all it can do. Let me do this. Which one is extract, David? Yeah, extract. So since last week, they released a new version of Mujoko. Here's the GitHub repo. So once you install it, so here I have the Windows version. There's also Mac and Linux versions. You want to execute simulate, and then you can drag in your model. I think we were working on that already last week. And then build a little something. I'm sure it works. So I made different scenes. This one will be the wall scene. So I built a climbing wall, a ground floor, and then we can run. I put in the Taiwan bear and the OP3. So this is the actual simulated model for the OP3. and then you can click run. And then, as you can see, because I wanted to see how realistic movement is, and then I realized there's this children's toy that you can actually build yourself, which is kind of like this, and then just goes down. So I was trying to redo that with an OP3 robot and rock climbing holes, and now it actually does that. You can watch it through this page. So for today's class, then you want to be able to import your own robot, the one that you build, at least the major outline. So you can also just start with, oh, that's interesting. The simulation there, usually it flips the last two still, but here the simulation is slightly different, which of course is not surprising. Also, after you've gone with after you install your robot, you can look at all the joints in the scene. So here are all the joints for the OP3 and the Taiwan Bear. And here are controls. So I can change the controls. So if I wanted to, what would I have to move? Shoulder, right shoulder, pitch. Oh, now it's moving a lot faster. Ooh. Here I can. Now he died. I mean, he didn't die, he fell off the wall. And I also have some climbing holes. I extended those in the Y direction now just to make sure that the sliding robot doesn't fall off. For the rear ones, they should be smaller. And those are all done using the Blender file. So if you go into this repository and go to models, then here are climbing holes in Blender. So then for today, see the groups.
I can't see again.
So let's see. Oh, oops. Did you touch something?
I thought something.
I think so.
But
Yes.
I turned on my computer, not your computer.
Well, you took my screen away.
Oh, so I cannot use this
No,
computer.
no, you can use it. I think you can use it.
Okay, now it works.
Teaching. So here I went to the climbing gym last week. Oh, okay. That's weird because I posted it on Discord. How come it says it's too big now? Copy image and then it's just strange. Block wall and okay, now it's happy. Weird. Okay, so here's one of the walls in the bouldering gym that gives you some ideas of what these roads can look like. For our first one, we want to use any one of the center holes. So I made a couple of them. That's weird. What did I do there? Oh. Oh. Okay. So yeah, so we have two different ones now. Now, to give you an idea of scale, that's my wife Ray Run. She's 1.58 meters tall. So up to this is 160 roughly. So then you can estimate how big the gap should be. And I can take that and export it as a object file, let's say. Oh, I did them already. We have job 1 center and job 3 center. And then here I can share my screen. Oh, no video yet on Discord. How come nobody told me? Yeah. Oh no, my video is here. It's this video. So the root would be the first one. So I'm just going to copy that one to make another root. E02. And these are the assets. Job 3 center. Move. So here are the two exported poles that allow center grip from the Blender file, and here you can put in the route that you're planning. Just one sentence everywhere. Job 3 recenter, reload. And my wall, the value 2 then. Wall C2. So yeah, this one is a lot smaller now, and we can reset it and you can see what happens to it for OP3. He climbs as well as I do. Oh, 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 ah! So now try and set this up, make the spacing between them a little bit smaller in the vertical. At the moment the difference is 35 centimeters, so maybe set it to 20 centimeters and make it go all the way from the bottom to the top of the wall.
I have another question.
Mm-hmm.
You posted a list with the group arrangement.
Pardon?
You posted a list with the group arrangement.
Yeah,
like
yeah.
last week. I'm not in there in this list.
Okay.
I was in the beginning and then I got stopped. There's someone else now.
Okay, then let me have a look at that list. We'll see what's going on now. So for the other students, you should contact your German students and see if you can work together with them in your group now, so that you can be prepared for the more interesting work coming up. And the list, where's the list? The list is, and go. But you two already have a Taiwanese partner, right?
Yes, Kevin is in the list. And I was there last
Kevin
week.
is in the list, but not you anymore.
I was there when you first posted it, but now there's.
Okay. Did somebody override it? I didn't get any messages.
Chinese guy who took our place in the Discord. Ah, so it's you who.
I've never seen that one in my life.
So you don't have a CD ready, right? So you're working in group 11 and 12.
11 and 12 shouldn't be
Yeah.
done.
Well, that's my fault.
Let me just see what I can do. Wow. Now my network is down. Um, okay, good. So let's see. So you're not in the merged groups anymore?
Sorry?
You?
I'm in 12.
You're in
I'm with Philip. In 12.
Okay. And you are with reason.
Yes. Just something.
Then we will make you guys. So it's you two, right?
Yes.
And you're also not on the list?
No, I can say accidentally his name is also in group 12 now. Something got mixed up. He's like in 11 in the list. He's in group 11 and group 12. And in the list in group 12, he took like my spot.
Okay. So Mark is in group 11, okay.
Yeah.
And how come you say he's there twice?
No, not Mark, George.
George.
You see the Chinese name on the Mark? It's like the same in 12 and 11.
Yeah, I'm in
Ah, okay. Okay.
Just documentation error.
Okay. But so who's Mark? You and you. And so actually group 11 is okay then, and I have to remove you from group 12.
Yeah.
And put in.
Also, I've never seen that number before in my life. I've never number.
Somebody told me that's your number.
I've never seen it before in my life.
I guess that's a secret Illuminati number. Before they send you off to the labor camp. Oops, I guess I shouldn't have said that. Okay, I cannot edit this right now. Okay, I'll do that. So I'll put in, what's your name then? Philip. Yeah. And the last name too? Where's Philip? Are you in my list anywhere that I can find it?
No. And this is?
No, not in the merged, but in the Taiwan groups.
Like
Mark. Philip Liebscher.
yes.
Okay, yes, then I'll put you in there. So then that 4 of you are okay. How about your group? You? Yeah, but you probably should, right? And And who is Larson Zorns? From NTNU, supposedly. Run J. Okay, so let me make sure that we can edit that through. So for the assignment, before I print out the details, part one, implement the computer vision algorithm. Done in groups of Australia and EU students. Implement the computer vision algorithm to extract position, orientation, and type of hand pulse from image. So that would be like this. Let's say. Part two, implement the motion planner for your home robot and the robot. OP3 or Oh, it didn't. So here's the simulation. Then you want to be able to implement the simulation in Mujoko to climb a simulated robot or your own simulated robot, and then your own robot on the climbing wall. And actually no OP3 here.
If you want,
And you can, David, you can just show the robot that you built so far to the camera, so students have an idea of what that looks like. That robot, if you just bring it up and hold it in front of the camera. Your leg there. Yeah. Oh, great. Just the leg. Yeah. Like this. So you can show it to the camera. Yeah. Like this. So this is kind of what it looks like. Yeah.
So after the task, the robot should be able to climb the wall.
Correct.
So we're done for semester.
Pardon?
So it's like, I thought that's the semester goal.
Yeah.
So this will be the task to end of semester?
Yeah.
this is
The hackathon is the last part of the semester.
So deadline for this task is December.
Just before Christmas. Yeah.
Oh. And if you
But it's
Are we doing some?
it requires some planning, and because you work together in groups, I want to announce that as early as possible.
Are German students building the robot in Germany as well?
No, I don't think so.
So they only help us with the code.
They will only help you with the simulation.
Simulation days.
so we don't do the simulation. We don't need to do the simulation.
You probably want to, the Taiwanese students should focus on the computer vision part for the students that are taking the computer vision course, and also building the physical robot and bringing the physical robot in the Mujoko simulation. The Ostfalia students, since they do not have their own robots, it would make more sense for them to focus on the simulation. Yeah?
So regarding the end goal of having a robot climbing the wall in real life.
Correct.
What wall and if is that an example of robot? I'm trying to understand how we're going to make it actually happen. Because in my mind, it's a really big jump. What's currently being shown.
We'll make the first wall will be something like this. The first wall will be something like what I simulated. Which is really not so much a wall as a ladder.
Okay, and the robot, again, like we'll make it out of those
Okay?
real life
这个只做了一个脚，所以你要做另外一个脚，就是做它的身体，全部都要做。好，这个之前对，那个是它的热气、过气，对，全部对啊，对，都好的。对，装好了全部，然后你又让如果可以爬，但是是约你是它模拟是给。我们想要做然后模拟是谁？我说那个模拟那个那个模拟不是我们做的，那个是德国的随身做的。一个给他们去操作，没有德国的跟我们的作业不一样，我们可以讨论， 因为他们是用模拟的，我们不用模拟，我们是做真的。那我们做手那要让它动，然后爬那个网上，
By external control means you
那
still
个应该
use
还有
our supervision algorithm.
Yeah.
This runs.
困难。
Correct. You don't need to run it. You don't need to run it on the keyboard.
Yeah, but external control doesn't mean we use the keyboard.
No,
Just
no. It has to be a process. But you don't need to bring all the processing and
等一下
power
我
onto the
他说
robot,
是
which makes a big
我
difference.
们不用让做那个 camera 对，是用 camera 的，我们不用做。那个这个机器人运作完了，它一定有一个头 camera， 然
No,
后
no,
让
no.
它看
The holes that
看
I
那个
built.
叫什么？就是那个
I mean, we can
那
change
个
those,
另外一
but
堂课
basically, if you have a
那
hook,
种
那个
会
wall 是
hook onto the
对，那个 wall 是另外一个学做，他做，
like a U
然后可是你还是
almost
要
like a
让你的 最后
these
把
are
它的
jugs,
结
so
果
they
就
look
是
kind of cohesive,
那个
almost like
computer vision
islands. When we did it
camera
before
有另外一
with
哦，我知道，
the
就是那个
Humanoid,
模拟
which
那个
is
computer。
a robot from
就是这一堂课就可以
12 years
computer
ago.
vision
我知道，我知道，早上
We were able to
他们
climb
没有
it,
学习
and
他们会
that robot
他们的作业
just used
你的
hooks.
作业
现场我们这边做出来播放，然后动，对，然后 tag 是那个早上有的，然后是那个
So just for the people that are convinced that this is impossible, there is precedent.
Okay.
But you have prepared the wall for the robot to climb.
Yeah,
The
yeah,
real
we'll build the wall. We have students working on this for their masters on a real wall.
Then I think it's better if the wall you give it to the computer vision student, so computer vision student will work with the real world, the real wall.
Yeah, yeah, sure. Yeah, once we have that, we take pictures of the real world.
We have to wait until the master student finish before we can get the.
We have to finish building the wall,
finish with
but we have the wall over in this lab. Yeah.
Okay. But I mean, we don't need to build the wall.
no.
We need to build the wall.
Yeah.
Kind of like this here, right? That robot just has hooks for hands. It's actually more complex and heavier than what we built today, and carries its own battery. But we use external power at this point.
Yeah. We only have to build the robots and the robots and algorithm that controls the robots. Do you provide us
And if it goes really well, we'll go to the climbing gym here in Taipei and try it on the real. And I did talk to them. So they say the minimum size should be about 50 centimeters. But if it's smaller than that, we won't be able to climb.
you provide us with like
So we just scale it down. We don't need to go to the real gym.
are we 100% free of the outside range servo models?
Pardon?
Are we completely free in designing the robot? Like
Yeah. Well, it should be humanoid. Like when I look at it, I must think that it's kind of a human shape.
I mean, it should have like certain size to be able to climb the provided wall. When it's like really compact and it can't reach the next hole.
Yeah, no, that wouldn't be ideal. No.
Yeah.
So the size that we target is about this 25 centimeters. Between 25 and 45.
If you said something about 16 servos. Or
16 servos is the maximum you want to use. Just because otherwise you run out of PWM channels.
Okay.
So you will have a lot of servo to provide for us.
Yeah.
Oh, okay.
That's good if you
The servos, we also just bought IMU units. So if you want to balance the robot, measure the
the orientation of the robot with respect to gravity, then we can do that too. But I don't think it's particularly useful for this assignment. I think it'll be enough to know where the holes are, and we make them relatively large so you can hook into it. Then you slide to the center position, that gives you a fixed location. Then 3 points, then move one limb to the next handhold or foot.
And hook in means you don't use the hand, you use like a hybrid?
Yeah.
Or, okay.
Yeah, we hook. You don't need to build a gripper. I think the gripper will probably make it much harder and very little benefit.
So the Mujoko only for the Germany student. We don't need to touch Mujoko.
Yeah, you have to get your robot into that simulation. And whatever you want to implement, your motion planner, you definitely want to test it out in the simulation first.
Okay. So let's say I can build the robot and then do all the motion planning without Mujoko, then I don't need Mujoko.
You could do that, but it would be an extremely risky approach because if it doesn't work, you have nothing.
Okay.
So first you would need to build the robot, like a real?
No, I think, yeah, but the real robot is, there's really only so many ways to put 16 servos together into 2 legs and 2 arms and a torso.
To get then we have to take the measurements to get it into Mujoko.
Correct, yeah. But Mujoko, after you've done this ladder, the next thing you want to do is use the Mujoko Pi, the Python bindings for Mujoko, which allow you to build things dynamically. So then you can just say, I have this servo, it rotates in this orientation, and the link to the next servo is 5 centimeters long. And then if it's not, you change it in your Python code to make it 4.5. Then it'll be very easy to adjust the simulation.
And should the robot start hanging on the wall? Or should it be
Yeah, we'll put him in the wall.
So
You don't need to walk up, but you need to take a picture of it first to figure out where the holes are.
so there's not, robot is not, has not to be able to stand by itself.
No.
It's only
It's not a, it is a humanoid robotics course, but I've done the course many times where we have balancing and walking gait generation, and we'll talk about those in class. But that's kind of a little bit boring, so we try something new this time.
So I can use the other
And
simulation.
the advantage of this too is that to do a walking gait is very dynamic. So if you want to develop that from the simulation, you need to be very accurate in your simulation. Otherwise, the sim to real doesn't really work. But if you can figure out the inverse kinematics of your robot, then the actual masses and everything are not that important, because if you have 3 points and you have enough torque to hang in there with those 3, the robot is going to stay in that location, independently of whether the mass is a little bit higher or a little bit lower. So in a sense, the rock climbing is much less dynamic than walking, so that will make it a little bit easier. Yeah.
Another question, in terms of like the camera, your vision card, does that have to connect to the robot, or can that
No.
be floating away just step out
No,
and
you
stay?
can use your laptop away from the wall. So basically, you'll have a picture a little bit more aligned than this, or the pictures that I posted from the on the Discord channel. So you don't have to use local vision. I think it will be an interesting problem because Obviously, if you're like this and you need to look for the hole, that would be a lot harder. You would need to do much better calibration and identification. And you could do more. You could do visual servoing, which would be also an interesting topic, but not something that I want to discuss in this course. And I honestly am not so sure how much that is useful for climbing. For the hands, I think when I climb, I'm pretty sure I look with where my hands go. But the feet, I think the feet, I just kind of know where to step, and then I hope that there's a foothold there. And there usually is, because I kind of remember the motion sequence that you're supposed to do. So the plan is the focus, in a sense, of the assignment is the actual plan. And by plan at the moment, we mean 3 points of contact. So 2 legs and 1 arm, or 2 arms and 1 leg at least. That always have to be engaged, right? So if you have those, then you have 1 limb free, either a leg or an arm, that you then want to move to the next hole. So then you have 4, then you can let 1 go, and then you can try and move that way. So there's nothing like the more elaborate, no dinos, no pogos, and nothing like that. Much more like a ladder than an actual climbing thing. We also have building a new 80 centimeter tall humanoid. So if we get a good algorithm for the motion planning, then that's the robot we would take to the actual climbing gym. But that one is a different robot that is built by other students. And that is the one that does everything on board then. But if we give it a plan, it should be able to execute that plan.
For simulation, Mujoko is the only. It's not the only option. I can use the other one. Like I can build my robot using URDF file and then put it in Gazebo or.
Yeah.
Isaac.
However, have you done any Gazebo programming before?
Yes.
Okay, because Gazebo is much heavier, much more heavyweight than Mujoko, and it takes my students a long time to get stuff into Gazebo, which is why I think Mujoko is actually pretty nice to use. Now, Mujoko, Isaac Lab both use the OpenUSD format. So if you have your environment in OpenUSD, then you can import it into either one. Mojoko I like mostly because for what you get, it's extremely small, 10 megabytes, extremely easy to install. Installing Gazebo is 1 week worth of work, trying to find the right libraries and everything. And then Gazebo Ignition or old Gazebo and all of that. And I don't even know if there's a new Gazebo one, maybe. And so yeah, I'm gonna work with Mujoko, but if you like a different environment better, or if you want to run it on massively parallel reinforcement learner using the NVIDIA RTX graphics cards, then you can use Isaac Lab or Gazebo or something.
Does Mojoko work with URDF?
Yeah. I think there's an exporter from URDF.
Yeah, we can export it. URDF to USD file.
Yeah. But I think it doesn't really matter because you don't have a URDF file of your robot yet either.
No, we have to build our robot.
Yeah.
So we need using URDF or USD. No.
Up to you.
Okay. So like I have to start from SolidWorks, build the 3D part, and then.
Not really. You can just measure the relevant.
Directly using URDF. Using the.
Directly go to the URDF.
Yeah.
If you have it in a CAD program, SolidWorks, Katya, whatever, then of course that part is easier. You can export the inertia matrices and everything.
Yes, I thought if we don't have the inertia and the mass, then we cannot work with the simulation.
It comes up with the default simulation.
Oh.
It generates some defaults for masses and convex hulls.
Even though we use our robot URDF. If we use our robot URDF, and then Mujoko will provide the
then
mass.
It takes the one from the URDF, of course. So there is an exporter for this. There's a viewer. There's URDF2 and Mujoko file.
Okay.
For Python package. So all the modern simulators nowadays support URDF files. So we're still waiting for the official description until we have the exact specification of the wall.
So in computer vision class today, you just ask us to practice with half circle, half line. It's just a practice, not real. We're going to use that.
You may or may not. That depends on you.
But we have from the master student the actual wall that we're going to use for real climbing robot.
Right, but you got that picture. That wall will be with different lightings and different routes. Like we will have more than one route on that wall. So you need to be able to take a picture from that wall.
You mean almost the same? Almost the same.
Like the computer vision part is definitely some version of this, either with the real wall or the simulated wall. Like I put 20 of those randomly on the wall. You should be able to tell me what the orientation and the type and the position is of all the walls.
Are our boards all going to be the same?
No. I plan on having 3 types. That are like either this. Actually, this one is kind of nice too. I like this one. This one, and then it would be this one. Rotate it by 45 degrees and then a different color. And I would probably scale it in X. for the simulation.
Okay.
So something like that. I'll try and give you 3 different sizes so that at least 2 different sizes so that it's a bit easier to recognize which type of hole. Also in the simulation, I tried to make this one quite flat, so if you extract the line, you can figure out exactly which position your gripper can, your hook can hold. But the important thing about this one is that for this kind of hold, if you look at it, then here your robot is not going to have any grip, right? If you put your hook there. So the hook has to be on this side. Now, if your center mass is down and you're hooking into with the hooks, the pirate hooks, then you will have a solid hold there, right? But on this one, if you're below your center of mass is pulling down, but it's at a 45-degree angle, you're going to slide off. So for that one, you would need to be, your center of mass would need to be to the left of this particular hole. Otherwise, you're going to slide off. If your center of mass, actually not your center of mass, if your torque, right, if you can apply force this way, then you're okay. You'll have grip. If your resulting force is acting the other way, pushing you the other way, you're just going to fall off. And then we will have 2. One center, one left, one right. So you are in my list though, right? Are you in the list of the group list? Yeah? The one on Google Drive? Yeah. Okay. Then it was just a mistake with your, so that can easily be fixed. Do you have a question or you're just practicing different holes?
I'm just imagining the robot.
Okay.
And also, you're using ROS2 for controlling the robot in simulation.
Me?
Yeah. No. How did you make the robot climbing? Where did you put your code?
This one, the one I did, is no code.
So how could the robot climb?
It can't. If you look at the video, where did I paste it? Here the robot cannot climb, but I thought I can get away with no control, just simulation, and use gravity. So he's climbing down, but he's just
fall down.
pulling up. Yeah, it's controlled falling.
But we won't do something like this.
No, you want to climb up.
Yeah. So how can we put the hold in Mojo Go?
You run it as a Python program.
Python program, not using ROS2 like nodes, publisher and sub.
You can if you want to, but that'll make it a whole lot more complicated.
So module code, just like we can control the robot.
Yeah, you can
module
control.
code.
The next step after you've done, if you show me the wall, the next step you can go and join and generate module code PY files. Which is the Python binding for Mujoko, and then you can have it usually starts with a text file. Instead of having a file, you have an XML description of the world, of your robot, yes. You just incorporate that, which is basically the same thing that you would generate now for Mujoko, right? It's all in XML. And then you can run the program, you can start the viewer, and you can send different control commands to the joints that you define. So then I just run this.
So you mean, I'm sorry, you mean basically like the robot description and the Python code, it is the same file. It's in the same file.
It could be the same file, yes. And if you use the Python code, you can generate it dynamically. So for example, even right now for the rock climbing robot, right? If you think about the kinematics of it, then I think the arms are okay. You want to be able to rotate this way, so you can lift it up and down. So you have 2 degrees of freedom here and 1 degree of freedom in the elbow, right? Yeah. And then that allows you to do this, allows you to do this, and allows you to do this. And that would be enough. Whether you align them like this one is 1, 2, and 3, or if you do 1, 2, and 3, the elbow is always like that. Elbow is always going to be here, but here you have a choice which way you want to orient those. So you have 3 joints here, 3 joints there, right? And I think that's minimum for what you want to do with arms. Then the tricky part will be, in order to climb up there, and in order to do the climbing, you kind of want to stay close to the wall, right? So if this is the wall, I want to stay close to the wall. If I don't have this degree of freedom, right, if I cannot do that, then it becomes very difficult to bend my knees and stay close to the wall. So I think the hip yaw is important, and so you probably want to have 3 degrees of freedom there, and you want to make sure that they don't interfere. Like if you look at the video from the Bioloid here, those motors are too close together, which is good for walking gait. You want that for walking gait, but you want to make them a little bit larger so that you can spin them like 90 degrees outside. I can actually do that. I don't know who's flexible enough. But these should be on the line like 180 degrees. Right? That will make the climbing a bit easier. If If you can't do that with your kinematic, it's still possible to climb, but it would be a little bit more difficult. And then you just have 1, 2, and the knee joint, so that's 3 plus 1, right? And then for the foot, I don't think I would do anything for the foot. I would just have a straight foot, no actuator. Because for climbing, I don't think the foot actuation is going to make much difference. So you basically have hooks for your feet too. And so then we have 4 here. Knee joint, 1. So then we have 4, 7 per side, 14 total. And then I do believe that for the torso could, so you could leave it at 14 and I think it'll be fine. If you're a bit more ambitious, you could try and put in a pitch and a roll joint for the torso. That one is actually probably going to be more useful for walking, but it'll allow you to lean over a little bit more. And then you have 16 degrees of freedom. And that, I think, is a reasonable kinematic set that you want.
Do we want to mount the Pico on the robot?
Pardon?
Do we want to mount the Pico on the robot?
You want to mount the Pico on the robot and then connect to it via USB cable, so you can send the commands, just like what you did with assignment number 1.
Do you have an example how you control anything via Python in Mujo code?
Yeah, sure. There are the Mujoko tutorials. Anyway, the reason why I bring that up is the robot materials that we use, right? The carport, everything can be cut very quickly. So it should be reasonably easy to change the design. So you may not be sure about the exact design that you want. You may want to test out a couple of ideas in simulation. So then it would make sense to dynamically specify these things. Like here, the link length of your upper arm and the lower arm length, right? How long you actually want to make them. You can, if you write them as Python code, then that could just be a variable that you set, and then it will generate the kinematics. And actually, if you are if you really wanted to, you could have the whole robot described in your Python program. That Python program generates a SolidWorks file and the Mojoko simulation file and what you need to cut out to build your robot, or the 3D printer G code.
So you say we can make a robot description using Python code, not XML.
Yeah.
I just know that.
Actually, you still use XML. Your Python code generates the XML. Because your Python code will generate the simulation environment, but the way that it's sent to Mojoko is via the XML file. So let me just implement Mojoko Python version of Actually, I think I duplicate this one. This one is kind of nice. So that would be left over. So now I'm not sure. Do I have UV installed? Oh yeah, I do. So first, I'm just going to create a virtual environment for Python. Now, there's been many different ways of packaging. The most popular at the moment seems to be UV. Or what do you guys use to start virtual environments in Python?
I'm just still using Conda.
Conda, yeah, that's popular. That's a little bit too, I haven't used it in a long time because it's a little bit heavy and I don't see the big advantages in it anymore, but yeah. So UV is some Rust program that does that, so we can create an environment for Mujoko and we can activate it. Oh, keyboard is wrong. Yeah. So we can activate it. Will be hit install Mujoko 5. So let's see. I switch my Discord. No, I switch my OBS. And that's that. And then, so here, this is a pretty standard workflow for using Mujiko from Python. You start out with a skeleton, which is your XML file, but it's included in the Python program as a string. Then this defines your world body. Then you can load it. You can also load a model from XML file, of course. And then it gives you the view of it. So we run this. Let's see what happens. These two tills. These two tills. Why do I need those? These two tills. And how come it's not installed here?
So it's just with those XML that actually
Oh, wait.
the whole.
No. Actually, let me try that. It may. No, it's in Mujiko. Hmm. No, it's not that. It's just Mujiko. Underscore file. See what Google says about that. Maybe a wrong version of. Hmm. Oh, yes, it's not. That's the problem. So we don't actually want Mujiko. I think it's Mujiko now. Just. try that again. P. Well, let's try that. So it's not Mojoko Pi, it's just Mojoko and now the Python language for Mojoko. Yes. Yeah, so this is the same tutorial that we did last time. Let me try and run this. So that at least didn't error out. Oh, actually, we did that last time. And then I had problems with the media. Because I don't have event tech. Yeah, so that's the same problem. And here you can calculate forward kinematics or like the forward simulation step, and then the actual render that you need to do. then I just can't show the video on this computer here. Yeah, let me see this if I can install media file. I think I can, but it won't do any good without the MPEG. Let's try that. And if you do it on your own computer, then it will be easier. You can just UV pip install media file. No, well, I've never seen this before. So the FFmpeg package, if it's in zip format, is 100 megabyte. In 7Z, it's 31 megabyte. So usually the compression algorithms are all relatively close. I've never seen 300% difference between using tar and zip and 7Z and all of that.
What is FFmpeg?
That's the video player for, it can do everything you want to do with the video. So the only reason they use it right now is so that it opens a window and it displays the video. It's annoying.
So you won't see the actual simulation in Humanoid?
No, it will open Mojoko for you, and the viewer is running and everything, but it doesn't have a window to display. So that's what it uses FFmpeg for. So you won't be using the XML version because then you cannot run the code. Like if you have Mujoko in here,
yes,
right, in this scene, then I can define things, I can move things around, but I won't be able to do things like, oh, if the balance is off by 3 centimeters, move your torso forward. Because XML files, by definition, are all static, and there's no way to attach a controller or anything to that. So that's why you need to run the I actually don't know what an MJV file is. But anyway, that's why you want to use the Python bindings. But unfortunately for them, so just so that you can show it, they need to have FFmpeg. So where is that now? Extract. Okay. Then take that. How about this plus D or Jackie? Oh, actually, probably not. FFmpeg essentials build. So here's the path. Oh, the console is really not very nice. And okay, maybe. So I forgot the semicolon here. And maybe no big, no trailing thing. D, Jackie, essentials build thing. Yeah, okay. Uh, and then install MediaPipe. So let's try and see if I can show it. Import media file and media, and let's import that because that's always useful. File dot sqlt, and then ah, it's for the Jupyter thing, for Jupyter notebook. So can I just call window again? That's right, that was the problem last time. Okay, so we need to use the launch passive. And then we need to delete the media file. model data. So here, then you can start your viewer from Python without the program stopping.
And XML string at the beginning will be our robot.
Yes, or the file.
So we could just import the XML file? Or
Yeah, you just open the XML file. I think there's from XML file instead of from XML string. And then that should be, oh, where am I now? Now I'm in
Are you able to import multiple files?
yeah.
For the wall, for
Yeah.
the whole thing?
Even if you look at the XML file that I wrote, the wall scene here, right, is actually very small because it includes the bear, the wall, the ground plane, and the root, and the OP3. So it's very nice to structure that. The one thing that I haven't figured out how to do yet, which you can do with Python, but one thing that I'm not sure how to do is, I would like the OP3, for example, is in this position at 000, right? In the include file. But when he's at the wall, I want him to be at a different position. So I don't know how to include it and then move the robot without editing the OP3 file. In Python, you can easily do that because you can load the model from the file and then just say model of position is 1111, then it'll move to that position. But with the XML files, I think there's a way to attach something to a geom, but I have not, because you want to use Python anyway, I haven't looked into that any further. Like, I'm sure there is a way, but I don't know how to do that. And here you can set some other things. So the actual scene is small. The root just includes the holes. The wall is just the background of the wall and the size of the wall and the height of the wall. And the bear is the bear, and the OP3 is the OP3. And now let me try this. So here you can have your geom and then copy it multiple times. Let me try and load from file.
Is it resourceful for running those simulations? Do you need like a lot of RAM?
No, it seems, compared to Ignition and iStack Lab, it seems extremely low. if I don't have a super modern laptop, but it works fine on a laptop. Isaac Lab, now you need to have an RTX. What's the minimum, David? I think
4
RTX
gigs
4? No,
4 giga RAM for the every RTX. Minimum 4 giga RAM.
no. We had to buy a new laptop now because according to Saeed, the PCs that we have, which all have more than 4 gigabytes of GPU memory, none of them were able to run Isaac Lab. What did I want to? I wanted to load something. So let's load the MP3, OP3, or load the wall. Why not? So that would be. And you can even run two at the same time. Like sometimes I run the simulation, two multiple sessions at the same time. This from XML path. So it puts the balls in there. Doesn't give me an error, but also, because maybe because I don't have any light. I think that is the wall. Yep, that. Oh, there's some options here that are kind of useful, which I didn't notice until a while ago. This one is kind of cool. You can generate frames for the body and labels and So yeah. No, it doesn't render those. You can also turn off gravity if you don't want your robot to fall off the thing, and show the masses, the center of mass, which is useful for the climbing robot to visualize that. Ah, okay, that's why they were as a kind of. Yeah. I'm not sure why wireframe was on. I selected. Yeah, here. So here you can set flags for your renderer, and in this case, I want to turn that off. So this is actually quite nice to use and powerful to visualize different parts of this. And now, let's say I have that. That's my wall. So I mean, I guess in theory I can load a OP3. Maybe. Can't be that easy. These are not actually from the model, they're just added to the viewer.
Yeah, so was last week. And I think after the sun, he will post
Today's video.
yeah.
Thank you.
The best. You know this guy?
No? Honestly.
You can do it.
Yeah.
Should wait, I can send you the
I very proud.
I think. You know the setup, you know?
Yeah.
Just have to figure out the
At least you know what to do.
yeah.
The first step to do the sound or set up everything so that you can build the wall and our own robot.
Yeah.
Easy. No, just kidding.
That's the spirit, easy.
No, that's very hard.
Yeah, I think you have to generate the XML stream because it actually compiles it. So you cannot add extra objects into the physical domain without without recompiling the model. So I think here the only thing I can do is load the entire model. And then we're going to call it wall scene 2. And now we have the viewer. Oh, there's my robot just came down. Oh. However, now it's under control of your Python program, so you can add additional things that you want to make. So if you let's try something simple. The balls, okay, we can add those. And then I can say model model.geom. What did I call the geom mesh body link. Actually, let's just print this quickly, see what information it puts out. Yeah, it's a function, not a access. Jerk, link. Oh, it didn't load it. No, it's falling down, so it should be loading it. MP3 on the wall. What is MP3? What did we load? Wall C1 or C2? Oh, it's not a geo, right? It's a body. Yeah. So, okay, so here's all the data you get for a particular body with all the children and everything. Now, if I look at the simulation and run it like that, this actually does feel slower than Then you see one of the problems is the holes, I made them very small, so it actually falls off the wall and then it just scratches, right? It doesn't keep going like this. So let's see. Uh, Maybe we can fix that. By saying model dot body length dot position. So here I can get the position data. By forcing him to always be at the same y coordinate. So now he cannot fall backwards or forward, just right and left. Up and up, right and up, but not away from the wall. No, I don't think that worked. And turn off the print because it's slowing you down. Here. I need to use data, not the model. Data. it's not that easy to just keep him that way. It drops off. So MJ step should be the okay, let's see if we change the color. Let's try that. So what's the geom of this body? Mesh. Oh, they're all. So now I can change the color randomly of my torso. It didn't take the position update, but it becomes a disco robot now. And this one here should be body link geo. just to be consistent with what they're doing. Unfortunately, actually, I may print this and see. Oh, this has position. Ah, yeah. Now I should be able to check. Sorry, buddy. So yeah, position we cannot identify like that easily. We need to actually apply a force to it to push it into the wall if I wanted to. So actually, what we can try is so for XML coming from there. With this file as F. We can read the file, and then I can do XML equal to. Let me try that quickly. So I can specify what the gravity is. Should be 0, 0, negative 2, negative 1. I think that's and then string XML. Oh, yeah. Okay. So I'll leave it at there for that for now. Let me just put that in the file. And -3, and then I can just load it the XML file. Simulate. Okay. What happened to my robot? Oh, he's there. How did he end up there? Oh, gravity is going the wrong direction. No wonder my coordinates. No, that doesn't change much. Okay, now it's just stuck against the wall because 30 Gs are just pushing him against the wall. That would make climbing easy though, right? So maybe a little bit too ambitious. Well, 10. Okay, it's moving a little bit too much. 7. Ah, now he's off. Oh, but the bear also drops in that direction. Yeah, no. Yeah, now he's. Now he's stuck on the foothold there, so he doesn't swing through the way that I want.
Excuse me?
So I thought maybe left hip pitch. Yeah, see? I just had to get the legs out of the way. So these are the individual joints that you can control, or you can read the left hip pitch. Oh, now he's pushing against the wall. Wow. Okay, now for the reason why we're doing, one of the reasons, by the way, why we're doing this model with Mujoko is because in the old days, the traditional approach to solving these kind of problems would be to come and develop a control algorithm, LQR controller or PID controller or something, in order to solve your problem. Nowadays, reinforcement learning is the king of the hill. So in order to do reinforcement learning, you need to get the model into a simulator, right? Because you're not going to run 100,000 trials with your real robot. Even if it wouldn't break, it would be impossible to time-wise to just do that. So I think it's actually an interesting challenge to have a robot that is not constructed based on CAD model from Katia or Fusion 360 and try and get that into a simulator and then see how accurate do we need to make the simulation so that the behavior that we can learn using reinforcement learning is still useful in the real world with the real robot. But that's it for today.
What's going to happen next week with the midterm exam?
Midterm will be without the German students.
So it's going to be like paper?
Oh, sorry. Yes. So the midterm is open book, open internet. You can bring your laptop, your computer, whatever you want to use. And I will post a sample midterm tomorrow. The exam is administered using GitHub, so it's a GitHub repository. So you must make sure that you have a GitHub account. And you fork the repository, and then it's all questions. You need to, there's like several files, question 1, question 2, question 3. A lot of them require you to write code or generate some output using a program. And then once you're done, you commit that and then do a pull request to the exam to actually submit it. But it's all done electronically. You don't need to write anything on paper. And the kind of questions would be for kinematics. This is a kind of robot. These are the joint angles. Where does the end effector end up? Or what's the rotation matrix? And my My thinking is always that in computation, we basically have three components. We have an input, we have an algorithm, then we have some output. So for homogeneous coordinates, you can say translations, okay, then you have a set of input points, you have a translation matrix, you have a set of output points. And the easiest kind of question would be to say, here's the input, this is a translation matrix, what will be the output, right? That's the simplest type of question. You can also ask, here's the translation matrix, this is the output, can you reconstruct what the input looked like? Can you do that? Is it unique, for example? Is there more than one solution? Something like that. And if you have input and output, then you can ask, okay, what was the transformation matrix that was used in order to map these points to those points? And that's basically it.
But there will be a sample tomorrow.
Pardon?
There will be a sample tomorrow.
Yeah, I'll post the GitHub repo. The GitHub repositories. I used to do it. Actually, I used to have it much nicer set up with HTML file. You would just open an HTML file in your browser, and then there were like boxes. You would type in your question, and then you can submit. It would automatically send it to my Discord server and put it in the database via the Discord messaging, and everything was run in the browser. So I actually liked that system. I thought that was pretty clever until Discord shut down the Discord JavaScript project that you need to run in the browser to be able to do that. So then all of a sudden that didn't work anymore. So now I think GitHub is more stable than Discord. Even though Microsoft bought them, they don't seem to change that much. Like git push, git pull is not going to change that dramatically.
And it's going to be Python coding, or
Actually, it's up to you, but depending on yeah, I'll ask you to run a simulation. You need to generate some plots. Then probably that's a lot easier to do in Python than unless you're an expert in Julia or something. I don't think Python would be a bad choice. I do think Python is a good choice. I don't think Python would be a bad choice. Yes. I just need to make sure my double negative